Complexity is generally used to characterize something with many parts where those parts interact with each other in multiple ways. There is no absolute definition of what complexity means. The only consensus among researchers is that there is no agreement about the specific definition of complexity. However, a characterization of what is complex is possible. The study of these complex linkages at various scales is the main goal of complex systems theory. In science, there are, as of 2010, update, a number of approaches to characterizing complexity. This article reflects many of these. Neil Johnson states that, even among scientists, there is no unique definition of complexity, and the scientific notion has traditionally been conveyed using particular examples. Ultimately, he adopts the definition of complexity science as the study of the phenomena which emerge from a collection of interacting objects. Overview. Definitions of complexity often depend on the concept of a system, a set of parts or elements that have relationships among them differentiated from relationships with other elements outside the relational regime. Many definitions tend to postulate or assume that complexity expresses a condition of numerous elements in a system and numerous forms of relationships among the elements. However, what one sees as complex and what one sees as simple is relative and changes with time. Warren Weaver posited in 1948 two forms of complexity: disorganized complexity and organized complexity. Phenomena of disorganized complexity are treated using probability theory and statistical mechanics, while organized complexity deals with phenomena that escape such approaches and confront dealing simultaneously with a sizable number of factors, which are interrelated into an organic whole. Weaver's 1948 paper has influenced subsequent thinking about complexity. The approaches that embody concepts of systems, multiple elements, multiple relational regimes, and state spaces might be summarized as implying that complexity arises from the number of distinguishable relational regimes in a defined system. Some definitions relate to the algorithmic basis for the expression of a complex phenomenon or model or mathematical expression, as later set out herein. Disorganized complexity versus organized complexity. One of the problems in addressing complexity issues has been formalizing the intuitive conceptual distinction between the large number of variances in relationships extant in random collections, and the sometimes large, but smaller, number of relationships between elements in systems where constraints simultaneously reduce the variations from element independence and create distinguishable regimes of more uniform, or correlated, relationships, or interactions. Weaver perceived and addressed this problem, in at least a preliminary way, in drawing a distinction between disorganized complexity and organized complexity. In Weaver's view, disorganized complexity results from the particular system having a very large number of parts, say millions of parts, or many more, though the interactions of the parts in a disorganized complexity situation can be seen as largely random. The properties of the system as a whole can be understood by using probability and statistical methods. A prime example of disorganized complexity is a gas in a container, with the gas molecules as the parts. Some would suggest that a system of disorganized complexity may be compared with the simplicity of planetary orbits. The latter can be predicted by applying Newton's laws of motion. Of course, most real-world systems, including planetary orbits, eventually become theoretically unpredictable even using Newtonian dynamics, as discovered by modern chaos theory. Organized complexity, in Weaver's view, resides in nothing else than a non-random, or correlated, interaction between the parts. These correlated relationships create a differentiated structure that can, as a system, interact with other systems. The coordinated system manifests properties not carried or dictated by individual parts. The organized aspect of this form of complexity vis-a-vis to other systems than the subject system can be said to emerge without any guiding hand. The number of parts does not have to be very large for a particular system to have emergent properties. A system of organized complexity may be understood in its properties through modeling and simulation, particularly modeling and simulation with computers. An example of organized complexity is a city neighborhood as a living mechanism, with the neighborhood people among the system's parts. Varied meanings of complexity. In several scientific fields, complexity has a precise meaning. In computational complexity theory, the amounts of resources required for the execution of algorithms is studied. The most popular types of computational complexity are the time complexity of a problem equal to the number of steps that it takes to solve an instance of the problem as a function of the size of the input, using the most efficient algorithm, and the space complexity of a problem equal to the volume of the memory used by the algorithm that it takes to solve an instance of the problem as a function of the size of the input, using the most efficient algorithm. This allows to classify computational problems by complexity class. An axiomatic approach to computational complexity was developed by Emanuel Bloom. It allows one to deduce many properties of concrete computational complexity measures, such as time complexity or space complexity, from properties of axiomatically defined measures. In algorithmic information theory, the Kolmogorov complexity of a string is the length of the shortest binary program that outputs that string. Minimum message length is a practical application of this approach. Different kinds of Kolmogorov complexity are studied. The uniform complexity, prefix complexity, monotone complexity, time-bounded Kolmogorov complexity, and space-bounded Kolmogorov complexity. An axiomatic approach to Kolmogorov complexity based on Bloom axioms was introduced by Mark Bergin in the paper presented for publication by Andrei Kolmogorov. The axiomatic approach encompasses other approaches to Kolmogorov complexity. It is possible to treat different kinds of Kolmogorov complexity as particular cases of axiomatically defined generalized Kolmogorov complexity, instead of proving similar theorems, such as the basic invariance theorem, for each particular measure. It is possible to easily deduce all such results from one corresponding theorem proved in the axiomatic setting. This is a general advantage of the axiomatic approach in mathematics. The axiomatic approach to Kolmogorov complexity was further developed in the book and applied to software metrics. In information processing, complexity is a measure of the total number of properties transmitted by an object and detected by an observer. Such a collection of properties is often referred to as a state. In physical systems, complexity is a measure of the probability of the state vector of the system. This should not be confused with entropy. It is a distinct mathematical measure, one in which two distinct states are never conflated and considered equal, as is done for the notion of entropy in statistical mechanics. In mathematics, Krohn-Rhodes complexity is an important topic in the study of finite semigroups and automata. In network theory, complexity is the product of richness in the connections between components of a system. In software engineering, programming complexity is a measure of the interactions of the various elements of the software. This differs from the computational complexity described above in that it is a measure of the design of the software. In abstract sense, abstract complexity is based on visual structures perception. It is complexity of binary string defined as a square of features number divided by number of elements. Features comprise here all distinctive arrangements of 0, s and 1, s. Though the features number have to be always approximated, the definition is precise and meet intuitive criterion. Other fields introduce less precisely defined notions of complexity. A complex adaptive system has some or all of the following attributes. The number of parts in a system and the number of relations between the parts is non-trivial. However, there is no general rule to separate trivial from non-trivial. The system has memory or includes feedback. The system can adapt itself according to its history or feedback. The relations between the system and its environment are non-trivial or non-linear. The system can be influenced by, or can adapt itself to, its environment, and the system is highly sensitive to initial conditions. Study of complexity. Complexity has always been a part of our environment, and therefore many scientific fields have dealt with complex systems and phenomena. From one perspective, that which is somehow complex, displaying variation without being random, is most worthy of interest given the rewards found in the depths of exploration. The use of the term complex is often confused with the term complicated. In today's systems, this is the difference between myriad connecting stovepipes and effective integrated solutions. This means that complex is the opposite of independent, while complicated is the opposite of simple. While this has led some fields to come up with specific definitions of complexity, there is a more recent movement to regroup observations from different fields to study complexity in itself, whether it appears in anthills, human brains, or stock markets. One such interdisciplinary group of fields is relational order theories. Complexity topics. Complex behavior. The behavior of a complex system is often said to be due to emergence and self-organization. Chaos theory has investigated the sensitivity of systems to variations in initial conditions as one cause of complex behavior. Complex mechanisms. Recent developments around artificial life, evolutionary computation and genetic algorithms have led to an increasing emphasis on complexity and complex adaptive systems. Complex simulations in social science, the study on the emergence of macro properties from the micro properties, also known as macro-micro view in sociology. The topic is commonly recognized as social complexity that is often related to the use of computer simulation in social science, i.e., computational sociology. Complex systems. Systems theory has long been concerned with the study of complex systems. These systems are present in the research of a variety of disciplines, including biology, economics, and technology. Recently, complexity has become a natural domain of interest of real-world socio-cognitive systems and emerging systemics research. Complex systems tend to be high-dimensional, non-linear, and difficult to model. In specific circumstances, they may exhibit low-dimensional behavior. Complexity in data in information theory. Algorithmic information theory is concerned with the complexity of strings of data. Complex strings are harder to compress, while intuition tells us that this may depend on the codec used to compress a string. Any two Turing-complete languages can be implemented in each other, meaning that the length of two encodings in different languages will vary by at most the length of the translation language, which will end up being negligible for sufficiently large data strings. These algorithmic measures of complexity tend to assign high values to random noise. However, those studying complex systems would not consider randomness as complexity. Information entropy is also sometimes used in information theory as indicative of complexity. Recent work in machine learning has examined the complexity of the data as it affects the performance of supervised classification algorithms. Ho and Basu present a set of complexity measures for binary classification problems. The complexity measures broadly cover 1. The overlaps in feature values from differing classes, 2. The separability of the classes, and 3. Measures of geometry, topology, and density of manifolds. Instance hardness is another approach seeks to characterize the data complexity with the goal of determining how hard a data set is to classify correctly and is not limited to binary problems. Instance hardness is a bottom-up approach that first seeks to identify instances that are likely to be misclassified. The characteristics of the instances that are likely to be misclassified are then measured based on the output from a set of hardness measures. The hardness measures are based on several supervised learning techniques, such as measuring the number of disagreeing neighbors or the likelihood of the assigned class label given the input features. The information provided by the complexity measures has been examined for use in meta-learning to determine for which datasets filtering is the most beneficial and could be expanded to other areas. Complexity in molecular recognition. A recent study based on molecular simulations and compliance constants describes molecular recognition as a phenomenon of organization. Even for small molecules like carbohydrates, the recognition process cannot be predicted or designed, even assuming that each individual hydrogen bond's strength is exactly known. Applications of complexity. Computational complexity theory is the study of the complexity of problems, that is, the difficulty of solving them. Problems can be classified by complexity class according to the time it takes for an algorithm, usually a computer program, to solve them as a function of the problem size. Some problems are difficult to solve, while others are easy. For example, some difficult problems need algorithms that take an exponential amount of time in terms of the size of the problem to solve. Take the traveling salesman problem, for example. It can be solved in time. As the size of the network of cities grows, the time needed to find the route grows exponentially. Even though a problem may be computationally solvable in principle, in actual practice it may not be that simple. These problems might require large amounts of time or an inordinate amount of space. Computational complexity may be approached from many different aspects. Computational complexity can be investigated on the basis of time, memory, or other resources used to solve the problem. Time and space are two of the most important and popular considerations when problems of complexity are analyzed. There exists a certain class of problems that, although they are solvable in principle, they require so much time or space that it is not practical to attempt to solve them. These problems are called intractable. There is another form of complexity called hierarchical complexity. It is orthogonal to the forms of complexity discussed so far, which are called horizontal complexity. Bajan and Laurenta showed that complexity is modest and is a feature of the natural phenomenon of design generation in nature, which is predicted by the constructal law. Bajan and Laurenta also showed that all the optimality statements have limited ad hoc applicability, and are unified under the constructal law of design and evolution in nature.